BioVivacious. I'm Sebastian. BioVivacious is a YouTube channel dedicated to clear fundamentals of biosciences and make the subject exciting. We have made remarkable progress in understanding centrifugation. We looked at differential centrifugation, we have looked at density gradient centrifugation, etc. Now let us look at another very important topic in understanding density gradient centrifugation. That topic is how to prepare a gradient for density gradient centrifugation. So this session is going to discuss all about that. So what are the learning objectives of this session? So in this class, we will learn about properties of gradient materials. We will also learn about how to prepare various gradients, discontinuous gradient, continuous gradient, etc. We will also learn how to load your sample that has to be separated. So there are techniques, there are theory involved in that. And finally, we will also learn how to collect the fractions. This is going to be the overall outline of the class. Though we have seen the logic of density gradient centrifugation earlier, let us look at it once more. So the basic logic of this technique is if the particle density is greater than the solution density, you know that the particle will sediment through the solution. As simple as you drop a stone in water. So what will happen to the water? What will happen to the stone? The stone will sink. So therefore, if the density of stone is higher than if the density of water, so therefore it will sink. If the second point is, if the particle density is less than the solution density, so the particle will float through the solution. So you blow a balloon and drop it on top of a water, a lake, the balloon will float. It will not sink. Okay. And the third logic is when the particle density is equal to solution density. So therefore, the particle, it will stop sedimenting or floating. Okay. It will be wherever it is matching, it will be there. So this is the logic which is being applied in density gradient centrifugation. Keep this in mind throughout this session. So which are the different types of density gradients? So there are three basic formats. So in the first format, the first figure is a density barrier. So density barrier, as the figure suggests, it has got two layers. So one is a very heavy layer, other one is a very light layer. So therefore it forms a kind of a barrier, density barrier for a molecule, a sedimenting molecule to move forward. In the second figure is what we call a discontinuous gradient. So a discontinuous gradient comprises normally about 3 to 5 layers of different density. You can see that in the figure we have 4 different densities. So from top to down it is in increasing order. But there can be discontinuous gradient as many as 12 different layers. So that is discontinuous gradient. And the last figure is the continuous gradient. So what happens in a continuous gradient is the density increases smoothly, okay, from top to down. It will keep on increasing and it increases in a linear fashion, okay, and it is very different from the discontinuous or the density density barrier type, where the gradient is a stepwise increase, whereas in the continuous case it is smooth increase of gradient from top to bottom. Let us look at the advantages of a density gradient. So several advantages. The first one is in the steep gradient beneath the layer of a sample suppress a premature sedimentation. Okay, so think of yourself jumping into a very deep sea. So you know that you can go only up to certain depth naturally. Afterwards, however you try, you will not be able to go down. However good a swimmer you are, you will not be able to go down, because when your density matches with the density of the sea water, you will not be able to go down. So therefore, in a centrifuge tube, if the layer beneath, it will prevent any premature sedimentation. That is one of the biggest advantages. And the second advantage is a steep gradient also minimize the convection currents in the liquid column. So these two factors, okay, suppressing premature sedimentation and minimizing the convection current, so it will increase the efficiency of sedimentation. Um, In the continuous, a third one is the continuous increase in density is usually accompanied by an increase in viscosity. As the solution goes down, the viscosity also increases. So it slows the fast moving particles and provide a better resolution of the bands. So as the viscosity increases, molecule will find it difficult to move. Only those molecules with the same density only will get aggregated. So and in increase of viscosity also decreases the diffusion. So therefore, they will all will remain together. So these are important advantages of a density gradient. So let us look at how exactly a discontinuous or a density barrier gradient is prepared. So first of all, we need to take the centrifuge tube and we start adding very slowly the highest density gradient first. So first the highest, let's say that 40% sucrose is the highest density we are going to use. So 40% sucrose solution will be taken into the centrifuge tube first. So it is normally added through the side of the centrifuge tube by using, there are many mechanisms available. You can use a similar laboratory, we can use a filler and we can load the sample. Once a 40% gradient is formed, then we add 30% above that, then 20% above that. So therefore, gradient is always poured from higher to lower density. So this is how we make a discontinuous or a density barrier gradient. A continuous gradient, normally it is a self-generating variety, this gradient materials. That is nature, that is a property of the material. So therefore, they are able to self-generate a gradient. So in a continuous gradient, the medium density varies in a continuous manner across the tube from top to bottom. Okay, or from in a rotor, if you are talking about from the axis of rotation to the end. So that is how the gradient will increase. This is a continuous gradient. Now, continuous gradients are classified as linear, exponential, and isokinetic. What does this mean? What do these mean? Three terms. So linear gradient, what happens is if the density increases linearly with the distance from the axis of rotation. So that is in the case of a swinging bucket rotor. Otherwise, if you are talking about a centrifuge tube, from the top to the bottom, the density increases linearly. So in an exponential gradient, the density increases or decreases exponentially across the rotor or in the centrifuge tube. So this will produce a kind of a convex or a concave shape. So if it is increasing, it will produce a convex shape. If it is decreasing the gradient density, decreasing the density, then it will produce a concave shape. So you can see the graph which is given below also for the exponential gradient. Now the third one is isokinetic gradient. So these isokinetic gradients are designed to produce a uniform sedimentation velocity throughout the gradient by counterbalancing the increase in centrifugal force. See, this will be experienced by the particles as the particle is moving towards the towards the bottom, or it is moving in an increasing density gradient or increasing viscosity medium. So therefore, this kind of an isokinetic gradient is made in order to have to counterbalance the centrifugal force, increasing centrifugal force, as well as the increasing viscosity of the medium. So these kind of isokinetic gradients are generally used in analytical rotors to study sedimentation behavior of particles. We can also make isokinetic gradient in our laboratory. A simple linear sucrose gradient loaded in a swinging bucket rotor is an excellent example of a isokinetic gradient. Look at the graph of this isokinetic gradient, how the gradient changes. So let us look at the resolution of a density gradient. So let us take first of all the density barrier. That is the first two figures. So in a density barrier, because of its very nature, it tends to produce a very sharp bands of material at interface or at the meniscus, or it will form as a pellet. Okay, so uh, continuous gradients are supposed to, you look at the last figure, continuous gradients are likely to provide the highest resolution. So the bands may be very broad because the particles can be very heterogeneous. Okay, so and harvesting these particles can be made can be less easy. It will be very difficult. Density barriers can be used to isolate the least dense particles. Okay, so you look at the first figure. So they can be, and also it can be used for isolating the most dense particle as a pellet. You look at the density barrier example, how we are able to separate them. So beyond that density, the particles cannot migrate ahead. So this is how resolutions happens in a density gradient centrifugation. We know that we use a density gradient centrifugation to separate particles, and we separate them either on the basis of their buoyancy density or their rate of sedimentation. Now we have seen two kinds of gradient centrifugation. Let us look at rate zonal separation. So in rate zonal separation, if the function of the gradient is to provide a gradient of viscosity which improves the particle resolution and stabilize the column from a convection current. So what about isopycnic separation? There, the function of the gradient material is that maximum density of the gradient media is higher than that of the particle. Okay, then only separation will occur. So therefore, let us look at what are the characteristics of an ideal gradient materials. There are several characteristics. The first characteristic is it should be sufficiently soluble to produce a range of densities that are required. Like, we have seen sucrose solution. We should be able to make 60%, 50%, 40%, 30% solution. So it should be highly soluble. We should be able to make that. And second, uh, it does not form solutions of high viscosity. We know that high viscosity, the particles will not be able to move forward. It can create convection current. So therefore, it should not be highly viscous. Okay, so and it should not be highly viscous in the desired density range. The third one, it is not hyperosmotic or hypoosmotic when the particles to be separated are osmotically sensitive. Okay, suppose your particle is osmotically sensitive. If it is hyper or hypoosmotic, you know that either cells can burst or it can shrink. So therefore, to avoid damage happening to the particle which is going to be separated, so this gradient material should not be hyper or hypoosmotic. And the next characteristic should be solutions of the gradient should be adjustable to the pH and ionic strength that are compatible with the particle being separated. So for example, if the pH of the particle that you're separating is, let's say, pH 7, And so your gradient material should not have a very diverse pH, okay, like pH 4 or pH 11. So it can create a problem. So we should be able to adjust the pH of the gradient material. And it should not affect the biological activity of the sample. Suppose you separate mitochondria, you separate a particular enzyme, and if the activity is gone, so your experiment is gone. So therefore, it should not have any effect on the biological activity of the sample. Now, it should be non-toxic and it should not be metabolized by a cell. No side reaction should occur when the separation is happening. So, and it should not interfere with assay procedure or react with the centrifuge tube. So, our gradient material should not damage the centrifuge tube or no reaction should occur. It should not interact with the cellular components which you are separating. So if that happens, or when you separate your enzyme and when you want to estimate your enzyme, the gradient material, you may not be able to separate it fully. So that should not have a side reaction happening. Okay. Now, um, therefore it should be very easily removed from the purified product. We should be able to separate it. Suppose you have a sucrose gradient, you should be able to separate sucrose from that. That's it. And we should be able to autoclave it. Okay, and it should not be very expensive. And finally, we should be able to recover it. It is not use and throw. We should be able to recover for future use. These are some of the characteristics of a good gradient material. Now remember that there is no gradient material which will meet all these requirements. A very important concept is osmolality. So osmolality, in the context of separating biological particles, has to be attended, because see, the osmolality of mammalian fluid is somewhere around 300 milliosmoles. So this osmolality is the same osmolality that is created by the normal saline which we use in a laboratory. Now, high osmolality solutions not only remove water from the interior of the membrane-bound particles like RBCs or from mitochondria or from chloroplast, etc. They also remove water bound to macromolecules like DNA. So DNA becomes dry, dehydrated after its separation. So loss of water from cell will reduce their size, increase their density, and therefore what happens is it will affect the buoyancy and the rate of sedimentation. So therefore osmolality has to be given extreme attention. So in the osmotic effect on a cell and macromolecules, we can reverse it. Okay, but the error that it is causing in sedimentation, now it cannot be reversed. So this therefore this has to be, you have to think about it. Now several density gradient materials have been developed over a period of time. In the beginning time, scientists have been using sucrose solution or glycerol solution or cesium chloride, rubidium chloride, etc. But of late, several new materials have been developed. And these gradient materials can be grouped under 5 main classes. And they are polyhydric alcohols, polysaccharides, inorganic salts, iodinated compounds, and colloidal silica. So these are the 5 different classes of density gradient medium. So this table gives you an overall idea about the 5 different, this is not an exhaustive list, there are many more other things that are commonly used. It gives an idea about the different gradient material and the kind of use these materials have. Okay, now look at, for example, sucrose. In our laboratory, we use sucrose in order to prepare a gradient. So it is used for separating membrane vesicle, viruses, protein, ribosome, polysomes, chloroplast. We will use it for separating chloroplast in our laboratory. So different gradient materials can be used. So this is for us to have an overall idea about the gradient materials. Now let us look at another important topic, that is how to prepare a gradient. So this involves a lot of practical skill. Now a gradient can be made in many ways. In a simple laboratory where there are no high-ended equipments available, we can we can prepare gradient by using a pipette or a filler. So we take the highest gradient material first in the filler and bend in the centrifuge tube about 45-degree angle, and slowly, as the figure say, slowly add the gradient material one after the other, beginning with the highest gradient. First you put 40% sucrose solution, then you add 30% sucrose solution through the side of the tube without disturbing the first gradient which is already there in the centrifuge tube. This is one simple way to make gradient in our laboratory. If you have a high-ended equipment, there is an equipment as shown in the figure. So this is an equipment where it has got two chambers. On the left hand side, you have a chamber that has less gradient material with very low gradient. And on the right hand side, you have a high gradient material, highest gradient. And there is an opening from the low gradient to the high gradient. And you will see a stirrer inside. And this stirrer will be always continuously mixing the low gradient, which is getting mixed with the high gradient. And through the high gradient, there is an opening, there is an outlet, which is connected to the centrifuge tube. So therefore, you know that initially high gradient material will flow into the centrifuge tube. As the mixing occurs, low gradient will be layered on top of a highest gradient. So this is another way to make a gradient material for centrifugation. So this is a very symbolic diagram to show you how to make how the gradient, once it is made, how it will appear in a centrifuge tube. So you can see that the highest density is at the bottom and the lowest density is at the top. And right on top of it, you load the sample, the green color, the sample is loaded. And there is a table, just for your information. What is the density of the certain macromolecules? So Golgi apparatus, you will see that 1.06 to 1.10 gram per centimeter cube. Glycogen, it is 1.7. So therefore your gradient that you prepare, if you want to separate Golgi apparatus and glycogen from the same sample, it should have a range of 1.7 to 1 gram per centimeter cube. Then only this glycogen can be separated from Golgi apparatus. Okay, this has to be kept in mind while preparing a gradient. The last part in this discussion is how do we apply sample for separation. Now keep in mind that all gradient must be prepared in cold conditions and the temperature should be maintained. So temperature should not be a factor in not getting the separation. Keep that in mind. Normally, if the sample is mixed with the buffer and it is very carefully layered on top of the gradient layer. Okay, so this is an art. You need to develop that skill. Suppose if the density of the particle that you want to separate is matching with the density of the topmost layer, normally if the homogenate is mixed with that gradient and then it is layered on top of that. All this will avoid if the solution getting mixed up. So it is to prevent all that, these steps are taken. Now before we apply the sample to the gradient, we need to determine the sample concentration and the volume that has to be determined. So remember that rotor can support, or the centrifuge tube can support most samples if the ratio between the sample concentration, remember the sample concentration, and the starting gradient, that is the lightest gradient. So that has to be in the ratio of 1:10. Okay, so if the sample concentration is very high, what will happen is it will merge, it will get diffuse. So we will not get an accurate separation. So, and it is also the volume of the sample which is applied is, it's related to the cross sectional area of the gradient that is exposed to the sample. So it depends on the diameter of the centrifuge tube. So therefore you look at the table that is given below, it will give you a kind of an indication. If your centrifuge tube diameter is about 12.5 millimeter, then by convention you will be able to apply 0.2 ml of the sample in a tube. If the diameter of the centrifuge tube is 35 millimeter, then you can load about 2 ml of your sample per tube. So what happens if too much of sample, or too high concentration the sample is applied on the gradient? So therefore what can happen is um, it can cause broadening of the separator zones, and you will have very poor resolution. Suppose you apply very less sample, okay, then what will happen is it will be difficult to identify the separator zone, because hardly anything is there to separate. So therefore you need to follow this particular principle in applying the sample. So what we have seen so far, we looked at many aspects like what are the properties of a gradient material, which are the different types of arrangement that you can do, the three types of arrangement. Okay, so the density barrier, either discontinuous, the continuous. Now how to prepare a gradient material, so how do you load the sample? These are the things that we have seen so far. Now let us look at how do we collect the fraction. Once you complete centrifugation, now comes the most exciting part of it, that is to collect the fractions. There are several ways to collect fractions. Let us see some commonly used method for collection of fractions. In the first one, the first method is talking about you can freeze in the separator fragments. Freeze the fragments, and then you cut that portion. That means cutting including the centrifuge tube, you can have to cut and remove it. So this is one way. So remember that this is damaging the centrifuge tube. In the second way, that is a figure B, the second way is again damaging the centrifuge. What you need to do is, if you cannot freeze the fraction, so create a puncture at the base of the centrifuge tube, and then allow the heaviest density particle or the density medium to flow through. So similarly, you keep on collect and discard. Collect only that fraction where your particles of interest is there, that got precipitated. Collect that. That is the second method. The third method to collect a fraction is, uh, see, there is a small gadget coming. And with this gadget, you attach on top of this centrifuge tube. And remember, the heaviest density is at the bottom. So fill in, pump in another still heavier than that. So you know that when you pump in heavier than that a density material, so it will slowly rise. The lightest material will flow out through the in the figure you see that out, through that it will flow out till you keep on filling the heaviest density till the precipitate of your interest is pulled out of the centrifuge tube. That is another method. And the last method is a very simple method. Bend the centrifuge tube and use a filler, slowly pull, pump out either supernatant. and separate in your pellet and transfer to another centrifuge tube. So these are the methods by which fractions can be collected.